Hello everybody, my name is Omar and I am a developer at RDX Works. In today's webinar, we're going to be building some of CryptoZombie's contracts on Radix. We will first begin by talking about some of the problems that exist currently with DeFi, and then we'll talk about what Radix and Scrypto are and how they solve some of the problems that we discussed in the first section. We will then take a look at a more practical example. We'll take a look at CryptoZombie's contracts. We'll describe what these contracts are, the responsibility of each contract, what each contract does and what it doesn't do. And then we're going to choose a specific contract from CryptoZombies, and we're going to build that on Radix using Scrypto. There will be a Q&A session, but we will do this Q&A session at the end of the webinar. And so if you have questions, you can either save them to the end of the webinar, or you can put them in the chat and I'll get to them by the end. So who exactly is this webinar for? This webinar is not going to be too deep. We're not going to be talking about deep consensus stuff. We're not going to be doing any complex mathematics. This webinar is mainly for people who have some Web3 experience or programming on Web3 and who wish to get a taste for what Scrypto feels like. And it's also for people who have already tried Scrypto out and wish to go a little bit deeper and wish to know some of the theoretical stuff behind Scrypto. And so these are the two main groups. If you've programmed in the past using some kind of Web3 framework, or if you're somebody who knows Scrypto already and just wants to know more. There are some assumptions that I have going into this. I'm assuming that you have already installed the Rust and Scrypto toolchains. If you haven't done that already, then here's a QR code. This QR code takes you to a page that has instructions on how to install Rust and Scrypto. I am making this assumption since I assume that some of you would want to follow along with the live coding that we'll be doing later on. Some of you might not want to actually follow along and are okay with just watching, so you would not need to install Scrypto in this case. However, it is useful to have. I'm also assuming that you have some programming experience. I haven't made any assumptions on what programming language you have used, just that you have some programming experience. You know what a function is, you know what a variable is, since we'll be doing some live coding and some programming experience is going to be very useful. So let's actually begin with today's webinar. So what are the problems that exist in today's DeFi? Well, there are two main problems. The first problem is that the builder experience is terrible. It's easy to build very simple things in Solidity, but very complex and very difficult and very time consuming to build any real financial applications in Solidity. And I think that this is evident by the amount of hacks that we see in EVM chains when we see stuff built with Solidity. A week or a month doesn't go by without us seeing 130 million being hacked, 200 million being hacked, and sometimes more. And I don't think that the next generation of finance is going to, I don't think a lot of people are going to believe that this is the second generation of finance when they see the frequency of hacks, how difficult it is to actually build things using these platforms. I do not think that this is the second generation of finance. The second problem is that all of the platforms that we've had so far have been very limited in capacity. And if you remember during 2021, 2022, or even 2020, Ethereum was running at capacity for a few months, and even Solana was running at capacity for some time. And all of the different platforms that we have at the current moment of time are limited in capacity. And when you have a platform limited in capacity, you have people fighting to get their transactions through, the transaction fees going up, and then it ends up, and then you end up in the situation where you have to pay $400 to send $1. And these two problems are essentially the biggest obstacles in the way of DeFi at the current moment of time. People do not have trust in this being the next generation of finance when they see the amount of hacks happening. And people do not have trust in this being the next generation of finance when they have to spend $400 to transact $1 when the chain is just congested. And so these are the problems that exist at the current moment of time with DeFi. And so with Radix, we try to solve these two problems. The first solution is that our platform is built for builders. We introduced a programming language called Scrypto, and we have our own virtual machine or execution environment called the Radix engine. These two work together to provide you with the fastest path from an idea to a production-ready DeFi app. In addition to that, we have our own consensus mechanism, which we call a braided cross-chart consensus. This is a linearly scalable consensus mechanism that has been already peer-reviewed. And the meaning of linearly scalable is that the more nodes that you add, the more that this scales. And so adding more nodes means more scalability, and all of this has been peer-reviewed and has been proven. And so these are the two ways that we plan on fixing the two problems that I just told you about. And so quick summary of what exactly Radix is. Radix is a layer 1 network that is purpose-built for DeFi to unlock its true potential through unlimited scalability, security, and asset-oriented programming. And so this is what we are and what we offer. So let's now switch gears a little bit and take a look at Crypto Zombies and take a look at the different contracts that Crypto Zombies has. There are three main contracts in Crypto Zombies. There is the factory system, there is the feeding system, and there is the front-end system. The front-end system is not a contract, it's its own JavaScript, HTML stuff, it's a front-end system. So in this Crypto Zombies system that we're looking at, there are two contracts and one off-chain system. The factory system is the system responsible for the creation of the zombies, for the creation of the random zombies. And the feeding system is the system responsible for determining the zombie that you get out when two zombies are combined together or when one zombie feeds on another zombie. The front-end system is the system responsible for determining how these zombies are displayed or how these zombies are shown. The on-chain aspect generates zombies with a random DNA. The DNA is just a number, a 16-digit number, and it is the responsibility of the front-end system to interpret what the 16-digit number is going to look like when rendered as a zombie. What we're mainly going to be looking at today is the factory system. We're not going to be looking at the feeding system, and we're not going to be looking at the front-end system. So today is only going to be on the factory system. However, for our more long-term collaboration with Crypto Zombies, we will also introduce the feeding system. We'll also take a look into the front-end systems and how all of those are done. But for today, just the factory system. So what we plan on building today is some contract or some blueprint, which is able to create new random zombies. For this, let's actually begin coding and let's actually begin taking a look at the code that we have today. I want to begin from some boilerplate code. I don't want us to begin completely from scratch. There are some functions that I've already written out, and there are some definitions that I have already written out that I would like us to use in today's demo. And so this QR code right here takes you to a GitHub repository that has all of the boilerplate code and all of the code that I would like us to begin from. And so you can have some time to scan this. Let me actually get my terminal up and running, and let me clone this. Let's actually begin. Okay, so I already have the repo cloned. So what I'm going to do here is go to the demo repo. And so this is what your repo is going to look like. As soon as you clone it, you're going to see three different directories. We want to go into the Crypto Zombies directory, and then we want to go into boilerplate. You should then open this directory up in your favorite code editor. I'll be using Code. I'll be using VS Code to open that up. And let me zoom in a little bit. All right. So as soon as you open this up, you're gonna notice a few things. And if you're somebody who is familiar with Rust, you're gonna be somewhat familiar with what you see here. There's a cargo.toml file and there's a source directory. And this is because Scrypto is actually a framework based on Rust. And this explains why you see all of these different things that you're used to seeing when you're doing any sort of Rust programming. It's because, well, Scrypto is based on Rust. And so the cargo.toml file has everything that you expect it to have. It's got a package, some dependencies, dev dependencies, a release profile, and some libraries. And then in the source directory, you're going to see a number of different files. Let's first begin by taking a look at the zombie file. In the zombie file, I've defined for us all of the different possibilities that a zombie could have. And so a zombie can have some head item, some eye item, some shirt, some skin color, eye color, and clothes color. And in here, I've defined the different possibilities that these things can have. And so the head item is some enum and enumeration, and these are the different possibilities that it can have. The eye item is this, and these are the different possibilities that it can have, and the shirt item is this, and these are the different possibilities that it can have. And I've also defined that a color is just going to be a U16 number. So I've defined for us what a zombie has, the kind of traits that it has, and also the different enums that it needs. One of the things I would like to note is in here, for the zombie struct, I have derived the non-fungible data. I've derived non-fungible data. So what does this exactly mean? When you wish to say that you're going to be using some struct as non-fungible data, when you say that you want to create a non-fungible from some struct, you have to annotate it with this derived non-fungible data at the beginning. And this is something that you need to do in Scrypto. I also took the time to define a number of pseudo-random functions for us. And again, these are pseudo-random number generators or pseudo-random generators in general. They're not true random. I've defined these since, as you can imagine, we're gonna be creating the zombie factory, which is gonna be creating new random zombies. In this, it's desirable to be able to create a zombie with, let's say, a random head, a random eye, or some random clothes, or some random shirt as an example. And so we need a way to create these pseudo-random numbers or pseudo-random enum variants. And this is exactly what this module provides us. Very specifically, I think that this is the main function that we're going to be using all of the time, which is pseudo-random enum variant. And this essentially allows us to create a random enum variant. So we can tell it, hey, we want to create a random head item, and it will create for us a random head item as an example. So this is the code that we have, and we're going to be designing our zombie factory in this file right here, the zombie factory file. So in this file, we see that we have something called a blueprint. So what exactly is a blueprint? So let me go back to my slides here, and let's talk about what blueprints and components are. A component is what you typically think of in Ethereum as being a smart contract. It holds some state, it has some data, and it has some methods that you can call. So if you think about it in the Ethereum way, this is what you typically think of when you say, I am looking at a smart contract. But the component does not hold any logic. The logic is actually held in the blueprint. And if you're somebody who's programmed in object-oriented languages in the past, the relationship between blueprint and component is going to be very apparent to you. You can think of blueprints almost like structs or classes, and you can think of components as being objects of this struct or class. And so the blueprint defines the structure, it defines the actual logic, and has the actual code, and the component holds the state but does not hold the code. If you're wondering why we do that, it's because you can have many different components instantiated from the same blueprint. When you think about ledger state and how much things are copied, it wouldn't make a lot of sense to say that all components copy the code, because the code is going to be the same in all components instantiated from the same blueprint. And therefore, it doesn't make sense to just copy the code from blueprint to component. Instead, it makes sense to say the blueprint holds all of the code, it holds all of the logic and the structure, and the component only holds the state, And yeah, if you have multiple blueprints, these get grouped into something that we call a package. Packages are addressable, components are addressable, however, blueprints are not addressable. If you wanted to specify a specific blueprint, you would do that by specifying the package address and the blueprint name. An example of where something like blueprints and components would be useful, or where the characteristics of these two things are useful, is let's say that you want to create some Uniswap clone. And what you want to do is that you want to have different liquidity pools for different tokens. So what you do is that you begin by defining a Uniswap liquidity pool blueprint. And in this Uniswap liquidity pool blueprint, you say, okay, I want to have two containers to store the two type of tokens I'm going to have. And these are the different methods and functions I would like to have. And then from this blueprint, you go ahead and you instantiate different components. And so from this Uniswap pool blueprint, we've instantiated a BNB XRD pool, an ETH ADA pool, and an XRD BTC pool. And so this is how the relationship between blueprint and component is useful. We did not need to have some on-chain factory contract to do all of that for us. All of this was done for us because all of these things are natively understood by the platform itself. And the kind of state that components can hold can be any string, any number, but it can also be tokens. Components can hold actual tokens inside of them. So what does that actually look like, and what does that actually feel like? Well, to explain that to you, I need to first explain to you what resources are. In Radix, resources are implemented natively and understood by the platform itself. And what this means is that tokens and assets are native to the platform itself. The platform knows that there's something called an asset, that an asset can be transferred, minted, burned, and all of these different things. The platform does not need any help to understand these different things. They're natively understood. And so if you compare and contrast this to Ethereum, this is a completely different approach from what Ethereum has. What Ethereum has is that there is one native token, ETH, and the EVM understands all of the rules that ETH follows, but the EVM doesn't understand that there could be any other tokens. Everything else is implemented as a smart contract, and people have come in and agreed that, hey, we're going to implement our smart contracts in this way. We're going to follow this standard for naming functions. We're going to follow this standard for naming methods, and this smart contract, if we do everything correctly, then this smart contract would act as a token, or would be considered a token. So with Ethereum, you need to define all of your tokens using smart contracts. With Radix, you do not need to do that. You do not define your tokens using smart contracts. When you have assets understood by the platform itself, you just say, hey, I want to create a new asset, and a new asset is created for you. And all of this is implemented through a finite state machine, and we'll be talking about the finite state machine in a little bit. There are two main types of resources implemented in Radix. There are fungible and non-fungible resources, and these mean exactly the same thing as other chains. Fungible resources are interchangeable and identical. Non-fungible resources are individually unique and individually addressable. And also, just to be clear, we call assets and tokens resources. And so that's the name that you're going to be seeing all throughout this presentation and all throughout this webinar. But resources always live inside resource containers. So let's now begin talking about resource containers and what exactly they are. So a resource must always live in a bucket or vault. It must always live in a resource container. Both of these are resource containers, and both of these can only hold a single resource address at a time. What this means is that you can have a bucket of XRD, another bucket of Bitcoin, and another bucket of ETH. However, you cannot have one bucket that contains ETH, Bitcoin, and XRD. So a resource container can only hold a single resource address. So how exactly are these two things different? Well, buckets are meant to be temporary and transient, When the transaction ends, buckets cease to exist and buckets cannot exist. Vaults are meant to be permanent and static. Vaults are meant to be stored inside of components, and vaults cannot be moved around. However, buckets can be moved around, and buckets are the main way of exchanging and moving tokens between vaults. And so if I wanted to sort of summarize the relationship between buckets and vaults in a diagram, I think that this is the diagram I would use. We've got two components. Each component contains a single vault. The first component wishes to send some funds to the second component, so it takes some funds out of the vault, puts them in a bucket, so takes funds out of the permanent resource container, puts them in a temporary resource container, and then passes them around to the other permanent resource container where these funds can be stored. And so this is the relationship between buckets and vaults. Let me now walk you through the finite state machine very quickly and tell you about what exactly it is, and then we'll talk about how you can modify the resource behavior on the finite state machine. So all resources are implemented through a finite state machine, and this is what the finite state machine looks like. So let me begin by showing you what actually happens. In the beginning, a resource does not exist, and it comes into existence by being minted. When a resource is first minted, it goes into a bucket. And if you remember, a bucket is a temporary and transient resource container. And now this resource has been created, it is now in a bucket. And then in the resource life cycle, it could perhaps then be deposited into some vault. It could perform the state transition of being in a bucket into being in a vault. It could then perform another state transition to go out from a bucket, to go out from a vault into a bucket. Perhaps it could then go into another vault again and back into a bucket again. And then this resource could perhaps be burned. If we no longer have any need for it or we have no use for it, it can then be burned. And so when a resource is in this state right here, there's only a finite set of things that it can do and a finite set of other transitions that it can make. When it is in a bucket, it can either be transferred into a vault or burned. When a resource does not exist, there's only one possible thing that can happen, which is it can come into existence by being minted. And so this is what the finite state machine looks like and how exactly it functions. The one thing I would like to talk about is how exactly do we actually modify the state behavior, or modify the resource behavior using the finite state machine. Well, we can do it by controlling who can perform the state transitions. Obviously, we do not want everybody to be able to mint a resource that we created. Obviously, we do not want everybody to be able to burn a resource that we created, or maybe we wish for that to happen. But what I'm trying to say is it is desirable to be able to control the behavior of the resource. It is desirable to be able to modify the behavior of the resource in some way. And so the way that we do it is by controlling who can perform the state transitions. In Scrypto, we can say this state transition can only be performed when this rule is satisfied, then this state transition can be performed. And so this is what it looks like. So one of the questions that you might have is, well, why exactly are tokens native to the chain, and why exactly are they implemented through a finite state machine? There are many different reasons for this. The very first reason is that it makes the idea of tokens very intuitive and very easy to understand. And I want to argue that a token really does not need to be Turing complete. Ethereum has Turing complete tokens, and the problem with Turing complete tokens is that they function more like black boxes. And what I mean by that is that you've got this token, or you've got this smart contract, and it says, I implement the transfer function. However, you have no trust in what the transfer function actually does. It says, I implement a mint function. However, you have no trust in what the mint function actually does. Having them as black boxes is really unintuitive and is really not something that you would want tokens to behave as. You'd want a token to be as transparent as it can be and to have guaranteed behavior. A mint is a mint, a transfer is a transfer, and a burn is a burn. And so all of these are advantages provided to us by the finite state machine implementation of resources. It makes them very intuitive and very easy to understand. It also provides higher guarantees and more transparency, which is one of the biggest advantages in my opinion. And one of the things that, one of the biggest advantages and one of the biggest reasons why this is an advantage is because you can take a look at a resource, or you can take a look at a token in an explorer, and you're gonna understand exactly how it functions. And so you can take a look at a resource and say, oh, this resource can be minted at some point of time, or this resource cannot be burned currently, but it can be burned in the future. All of these things are going to be represented to you in a very clear way, and this is because all of these things are finite state machine transitions, and we can very easily represent them to people since they're just finite state machine transitions. The different behaviors that you can control on resources are: you can control who can mint and burn the resource. You can control who can withdraw and deposit the resource. You can also control who can update the metadata on the resource. So metadata in this case is the, let's say, resource name as an example, the maybe the resource symbol as an example, and stuff like that. You can also control who can recall this resource. This is something that is not yet implemented, but is something that will be implemented in the future. In the future, people will be able to recall resources to say, I've given somebody this resource, I actually want to get it back. And there are multiple advantages to this, especially when you begin to consider the sort of power provided by the Scrypto badge system and all of this kind of stuff. And so as a user, if recall was implemented, it's very important for you to be able to say, well, I want to know if the resource that I have is recallable. I want to know if this can be taken away from me. And this is something that we aim to provide you. We aim to provide you with a way to be able to look at resources and determine how this resource is going to behave and how this resource is going to function. So we've talked for a while. Let's now take a look at some actual code, and let me show you that all of the stuff that we've talked about does actually map and does actually translate into code. The first thing I want to talk to you about is we said that there are two main types of resources, fungible and non-fungible. This is actually how you specify the type of resource that you want to create. Or actually, before going through these, let me actually tell you what this code here is for. This code is the code to use to create a new resource. So we're creating a new fungible resource. We're specifying some metadata. We're saying that this is mintable and burnable, and we're specifying some initial supply. In here, you can specify the type of resource you want to create. And so in here, we said we wanted to create a new fungible resource, but there is nothing stopping us from creating a new non-fungible resource. Also, if you remember the finite state machine, when we first talked about it, I told you that when a resource is first created, it goes into a bucket. And this is indeed what happens. When we first create a resource, the return type of that is a bucket. And so when we first create it, it goes into a bucket. If you recall, a bucket is a temporary resource container. Also, I told you that we can control who can perform the state transitions in Scrypto. So this is the way that we do it. We say that only somebody with an admin badge is able to mint this resource, but everybody can burn this resource. Anybody who has the resource is able to burn it. And so this is how the different theoretical things that we talked about during this presentation map into actual code. And so let's actually continue working on the crypto zombies or the zombie factory blueprint. I had to go off on this tangent to actually explain to you what a blueprint was. So now you have an idea that a blueprint is similar to a class in object-oriented programming. We also talked a little bit about resources and what they do and what they are and how exactly they're implemented. And so let's actually go back to code now and begin coding our blueprint. Every single blueprint has a struct and an implementation of this struct. In the struct over here, you define the kind of state that you wish to have. If you wish to have some permanent resource container, which is a vault, then you specify it here. If you wish to have some data that you store, maybe some string, some resource address, some component address, or something of some sort, then you store it here. So let's actually begin by implementing the Zombie Factory blueprint, and then we'll take a look at the kind of state that we wish to have. And so the very first thing I would like to have is some form of a constructor. I will call my constructor Instantiate New Factory. My constructor is going to take no arguments and is going to return a bucket. So let's first talk about what we intend the constructor to do so that you understand why it returns a bucket. We intend for this constructor to create the zombies token. And so we're building a zombie factory. The zombie factory is going to be creating zombies, and the zombies are going to be NFTs. And so we intend for this to, or actually it's not going to return a bucket. It's only going to return a component address. Sorry about that. It's only going to return a component address. Let me go back. We're creating a zombie factory. The zombie factory is going to create new random zombies, and when it creates new random zombies, it will mint an NFT using this random zombie and provide it back to the caller. What we wish for the instantiation function to do is to create this new resource for us so we can actually mint those tokens at a later point. So we can actually mint those tokens when people request them and when people want them. So the very first thing I will do, if you remember the code, I will say that I want to create a new resource. So I will say let zombies, and I'll say that this is equal to a resource address. So I will go to the resource builder. I'll create a new non-fungible. And for the time being, let me create the most boring non-fungible in the world. I'll say I want to create this new non-fungible with no initial supply. This is going to be the resource for the zombies NFTs. So let me now begin by providing some useful metadata to this resource. I'll call this zombies. I'll provide it a description. I'll provide it a description of this is a zombies NFT. And maybe I can provide it with some kind of symbol, and I can say that the symbol for this new resource I'm creating is, let's say, zombie. And so this is about it. And one of the things that we're going to need to do is that we're going to need to refer back to this resource address at a later point of time. And the later point of time is when people want to actually mint to mint a zombie, is when people are requesting a zombie from us. And so in this case, it would be useful for us to have this in the state of the zombie factory component so that we're able to retrieve it back. So let me say zombie resource address, which is just a resource address. And so now that I've created this new resource and I've created it with no initial supply, I want to instantiate my component. So I'll say the zombie resource address is zombies. Then I wish to instantiate and I wish to then globalize. So let's actually take a look at what the Instantiate New Factory does. Let's walk through it and let's see what it does. The Instantiate New Factory is meant to create a new zombie factory component from the zombie factory blueprint. It instantiates a new component from the blueprint. In the process of instantiating a new component, we would like it to create a new resource for us This resource will be the non-fungible resource, which we'll be using to mint zombie NFTs when we need them. And then we instantiate it right here, and we specify that the zombie resource address is zombies. In the zombie factory state, we have the zombie factory resource address here because we would like to persist that. We would like to have access to it at a later point of time when we need it. And so this is what this function does. We would now like to write the function that mints new zombies for us. So let me come down here, or let me actually do something here. I want to say that this is mintable, but I want to put a to-do comment here to say we're gonna be coming back to this later. I'll be coming back to this point later on. For the time being, let's just pretend that this doesn't exist. So we'd like to define a function that mints zombies for people when they request zombies. So we'll define a new function. We'll call it new random zombie. This new random zombie function returns a bucket, and if you remember, a bucket is a temporary resource container. So we would like this function to create a new zombie first and then mint that new zombie. And so the way that we'll go about doing this is by using some of the functions defined in the random module. We'll first need to, let's take a look at how zombie is defined. I'll put this to the side. A zombie has a head item, eye item, shirt, skin color, eye color, and clothes color. We will first like to begin by randomly creating or randomly generating a head item, eye item, and shirt item. So let me say random head, which is a head item, is equal to, and we're going to be using a function from the random module, which is the pseudo random enum variant. And let me actually call this head for simplicity. We'd also like to create a random eye, which is going to be an eye item. We'd also like to create a random shirt, which will be a shirt item. We now need to generate 3 random colors for the skin color. Eye color, and clothes color. So let me say let skin color be a color. And to generate a random number, and by the way, color is just a number, and it is a number. We intend that on the front end, it would be a number between 0 and 360. So from the random module, we'd like to use one of the functions that generates pseudo-random numbers for us. We'll use this function to generate a pseudo-random number for us between 0 and 360. Also generate an eye color and a clothes color. Let me see what error there is. Right, so in here I can say as U16, and so that is just some typecasting that we need to do because pseudo-random number generates a U128, but we'd actually like to have a U16. Not a problem, very small minor thing. So now that we've generated all of the random attributes that our zombie is going to have, let's actually create our zombie. So I'll say let zombie equal to a zombie. Say zombie new head, eye, shirt, skin color, eye color, clothes color, and this is the new zombie that we just created. So now we would like to mint a new zombie for the person who wants it and then return a new zombie for that person. In here, we have just created the non-fungible data, the data that the non-fungible token is going to have. We would now like to actually create a non-fungible token and give it to the user. So what I would like to do now is say borrow resource manager. You can think of the resource manager as being some kind of control panel that includes a number of useful functions for the resource. And one of the useful functions it includes for the resource is the ability to mint more of that resource, to burn some of that resource, and so on and so forth. So the resource manager includes functions to, as the name suggests, manage the resource. I'll do and in here I have accidentally forgotten. This takes an immutable reference to self. The reason why it takes an immutable reference to self is because this is a method and not a function. This is a method that exists on a component and not a function that exists on a blueprint. And so it actually uses the component state when being called, which is essentially what I'm trying to say. And the reason why it is an immutable reference is because no changes happen to the actual component state in the process. The only thing that gets changed is perhaps some of the stuff in the resource manager. However, the component state itself is not changed. So in here, I'll say that I would like to borrow the resource manager for this specific resource address, for the zombie resource address. I would like to mint a non-fungible. And when you want to mint a non-fungible, you need a non-fungible ID and some data. That's what a non-fungible is. It's an identifier and some data. For the non-fungible ID, I can just say I want to create a new random non-fungible ID. And I would like for my NFT to have this data. Let me look at why it's screaming at me. This needs to be a reference. There you go. Okay, so what do we have here? We've fully finished this function. Let's take a look at what this function is supposed to do, what it does, and all of that. The new random zombie function is supposed to create a new random zombie for us and then mint a new NFT using this random zombie that we have created. This function takes an immutable reference to self and returns a bucket. And inside of this function, what we do is that we generate some of the random traits that will be used for our zombie. We then create our zombie, and then we mint an NFT of this zombie. We mint an NFT of this zombie by borrowing the resource manager and then minting a non-fungible. Each non-fungible has a non-fungible ID and some data. In this case, we've specified that we wish to mint a new non-fungible with a random ID, and this is the data that we wish to use. Let's now go back to this because there's a bit of a problem when it comes to the minting here. If you remember, we talked about state transitions and when they can happen and all of that and all of these different concepts that we have on our resources. And in here, I left a little comment saying, hey, we got to go back to this because there's a little something that we need to go back to. We got to make this resource mintable. At the current moment of time, the resource is created, but the resource cannot be minted. And so we need to find a way to actually make this resource become mintable. And the way that we do that is by using something called badges. And badges are heavily tied to authorization and how exactly authorization works in Scrypto. So let's actually begin by talking about that, and let's talk about how this differs, how authorization in Scrypto differs from authorization in Ethereum and in other platforms. Authorization in Scrypto is based on what you have and not who you are. It is not based on your caller address. It is based on whether or not you possess some resource which authenticates you and allows you to perform some action. And so authorization in Scrypto is done through badges, which is what you have and not who you are. And when you use a badge, badges do not need to be passed around. Badges only need to be shown. When you want to tell a component or when you want to tell somebody else, I have authorization to do this, you do not send them your badge. You only need to show them your badge or show them a proof that you are in possession of your badge. And so I want to talk about the proof system that we have in Scrypto and what exactly it means. Let's say that we have some individual, And this individual owns 1,000,000 coins, 1,000,000 my coin, but he wishes to prove to somebody else that he is in possession of 50,000 of my coin. The only thing that he wishes to do is prove that he is in possession of this amount. And he doesn't want to do the primitive thing of sending the tokens and telling the person send them to me back, and then having to risk that he doesn't actually send them back. So what can this person do? Well, he can issue a proof of these tokens. He wanted to prove that he is in possession of 50,000 my coin, and so he produced a proof of 50,000 my coin. As you can see, the balance in here did not reduce. No tokens are actually stored in the proof. The proof does not store any of the resources. The proof is simply a proof that I do have this thing in my possession. I do have these resources in my possession. And I wanted to talk about proofs and how exactly they work and all of that because of this one point. A badge does not need to be passed around, only needs to be shown. When you work with badges, when you use authorization in Scrypto, you only need to produce a proof of your badge. You do not need to pass your badge in a bucket to some other component. And so this is how authorization works in Scrypto. And so let me actually scroll down a little bit. So let's actually continue coding. And before we continue coding, let's kind of devise a plan for what exactly we would like to do in this case. We said that authorization is done based on what you have and not who you are. And so we would like to create a badge, and we'd like to say that this badge is going to be stored by the zombie factory, and that only this badge is going to be allowed to mint the zombie tokens. So let's do that. I'll call this an internal admin badge. On the resource builder, new fungible, and I'll give it an initial supply. Sorry, let me give it an initial supply of 1. And this will go into a bucket. I would then like to say that the zombie factory components need to persist this badge, and they need to have it so that it's available to them in the future. So it needs to be stored somewhere. So we're going to store it in a permanent resource container or a vault. Now we need to say that zombies can only be minted if an internal admin badge is presented. So let's do that. Rule require internal admin badge.resource address, and would like this to be immutable, meaning that the minting rule cannot be changed at any point in the future. It is fixed and cannot be changed. Let's now update how we instantiate the component. Internal admin badge is a vault with bucket of the internal admin badge. Now, when we mint our resource, we need to present our badge to the system. We need to show the system that we are in possession of the internal admin badge, which is required to mint this resource. So the way that we do it is by saying self.internal admin badge or self.the-vault containing the badge.authorize. Authorize essentially says, I wish to show the system that I am in possession of this resource. And then inside of this, we mint our resource. And this is our zombie factory. This is about it for the code that creates the zombie factory. We've got an instantiation function and a function that creates new zombies for us. The function that creates new zombies is quite simple. It just creates some random traits, creates a new zombie, and then it mints a new zombie with authorization from the internal admin badge. And so we will now do a Q&A session based on everything that we have discussed here.